Yes, here we are. It's the physics video lecture. This is the fluid mechanics video lecture 1. So I'm going to get right down to it. The end of both of my standard mechanics lectures has started featuring some fluid mechanics, and we will do the first couple of lectures along those lines and then try to get into a little more depth, get some interesting topics there. So I'll start with that outline that I'd like to give just about the position of fluid mechanics within the rest of mechanics. And then maybe talk a bit about some of the topics that we would like to learn about. So starting with mechanics in general, we have point mechanics. So Newton's law, and the force on the ith particle, and just for the sake of some formalism we've seen before, we could, for example, say it would be the external force plus the sum over J Fij of all the internal forces. So yeah, that's point mechanics that we went through, that we go through. And from point mechanics, we can specialize to rigid body motion. Which is essentially a point system in which all the relative distances are fixed. If a body is not strictly rigid, we can actually have elasticity theory. And that's a really great subject in and of itself, that maybe we could do someday, not in this class. So we can do elasticity as a solid that's not purely rigid but somewhat deformable in how it responds to forces. And then we have fluids. Okay. Both of these theories actually involve similar techniques. They are more generally referred to as continuum mechanics. And they're very important in applications. Fluid mechanics has a really special place in terms of applications because it's used in many applications, but it's also formally sufficiently difficult that there are a number of unsolved problems that people actually want to solve. So it's still very fresh to get into there and learn about it. You never know who will play a role in solving some of these problems. The mathematicians have problems with it. And in applications, there are important problems all over the place, all the way from astrophysics down to very small fluid systems, where an understanding of, for example, transitions to instability are just desperately needed and impossible to get. So, and actually, to say a little more about that, other applications involve computational physics. Very, very active field of study, fluid mechanics, computational physics. So something for a lot of people. Okay, then, but we'll get to those things as we progress. So I'll just put up the characterization of the fluid, and then talk a bit about the types of problems we want to study in this short course. Remember, this is 1/3 of a semester, but so we'll still do some good stuff. Okay, so we're characterizing a fluid by a velocity field. That is to say, a velocity at every point in space. Oops. X, Y, and Z, and time dependent. So the goal is to completely characterize this velocity field of fluid flow. And we also need pressure, density. So we have to find differential equations that will involve these types of quantities and others as well are actually thermodynamic problems, and a rigorous derivation of the fluid mechanical equations requires a little bit of thermodynamics as well. So we'll do a bit of that just to make sure everything's well founded. So I'll just say thermodynamic quantities. Equations of state, and so forth. There are situations where it's simply possible to solve purely fluid equations, and other situations where these have to be brought into play. And I could add to these, temperature plays a really important role in some systems, and so forth. Temperature and entropy, and so forth. Okay. Adding to that characterization, since it's a continuum mechanics, there are also a couple of viewpoints. The idea is that if we take a little infinitesimal element of the size with which we can do calculus, the grain size is so small that we can do derivatives and stuff. On the other hand, this thing holds a bunch of atoms inside of it. Here, I'll use another color. So this volume element is, it's small on the scale of how this field changes, but it's large in the sense that it contains very many atoms. Okay, volume element contains, and by the way, we should call that the infinitesimal volume element. I'll write that down, because that's the kind of math we're doing. Infinitesimal volume element contains many microscopic particles. So that's one of the idealizations there you have to be aware of. And the second point, to number things, is that the forces are short range. The forces between volume elements are short range. Which is to say that if you have two little volume elements, I'll just draw a couple little cubes here, then their action on each other is via their adjacent surfaces. Okay, so short range forces. And those are assumptions that go into the background of everything here. So when we set up our equations, we won't belabor these things, but they're there. Now, as far as our goals, I was just thinking about this. If you look in your lower division physics book, it'll always have a chapter on fluid mechanics. And I've asked students before, I have a full semester's worth of notes here for a semester course that I taught before. And I did ask all the students what they knew about fluid mechanics, and they really they didn't remember anything, or maybe that hadn't been covered. So one of our goals is to cover the material that you'll find in the lower division, big fat physics textbook that you may still have. Lower division course. And hopefully we'll be able to tackle it more rigorously. So instead of just being given certain results, we'll actually derive them. So yeah, we're going to try to do that. That of course includes pressure, Archimedes principle, but also Bernoulli's equation, if that rings a bell. Bernoulli's equation we want to get, and viscous fluid flows. For example, pipe flow. In other words, for some of these things, the ideal frictionless fluid is good enough. But even when you get to a pipe flow, you actually have to have viscosity. And good, so that's one of our goals. But we want to do it at a more sophisticated level. So speaking of viscosity, we actually get a reasonable derivation of the Navier-Stokes equation, whose solution is sort of the holy grail of one branch of all of this, because these solutions are hard to come by. But yeah, we'll be able to talk about that when we get there. But yeah, definitely this kind of elementary material, because it has a lot of day-to-day applications. So Navier-Stokes equation, and I could just summarize a lot of stuff. Fluid instabilities, that's where we get into some really interesting terrain that we at least want to talk about and see the equations and what the difficulties are. So fluid instability, transition to turbulence. Still not understood. And other interesting things as well. Okay, so we have that. And I'll just start off with the initial conservation laws. Conservation of mass, and then Newton's law, and then we'll see where we go from there. So the conservation of mass leads to a continuity equation, something you also have in electricity. Conservation of charge leads to a continuity equation. So let's just start numbering things. Conservation of mass. Okay. The idea in a fluid flow, you can imagine it best in a constricted pipe, that the same amount of fluid coming in over here is present at all times. And the elementary version of this will just tell us that where this cross-sectional area is large, the flow is slower than it is where the cross-sectional area is small. Okay. So we want to get the formal cross-sectional area, there's a small, a large one. Yeah, so we want to get the formal expression of that. And we'll go straight to the integral. Go straight to the integral. Sure. And we'll talk about the fluid flow through a closed surface. So if we were talking about that, we could, for example, imagine we have this pipe and the closed surface has the intake on this side and the outflow right there. So that would be a fluid flow through a closed surface. And we'll write down the we'll write down the condition there. Basically, you're looking at, and since we're talking about mass, we'll write it down and we'll check the dimensions. Kind of about density times velocity through, we'll call D area. And this is a closed surface. So it's the boundary of a volume closed. So something like that. That would be the fluid flowing through a closed surface. Let's check first of all the units on this. Okay. So we have mass per volume. We have a unit of length, 2 more units of length, so that's volume. So that's mass, and the denominator of velocity is time. So this is mass per time right here, flowing through a closed surface. So that's the one side of an equation. Let's see how the other side is going to look. Ah, yes. Actually, we'll keep this same side here. We're going to keep rho v dot outer surface normal d area. We can do that as well. D volume. Okay. So yeah, it's just the same thing. Outer surface normal. Now this, since it's the fluid flowing, if this integral is positive, just imagine v and n hat being parallel, then this integral, under those circumstances, could be positive when fluid is flowing out. So you have a net outflow, and yet this integral is positive. That means this would be the negative of the change with respect to time of the fluid contained in that volume. So this would be density d volume. So mass per volume times volume is mass per time. So mass per time. So we got the units right on both sides of this equation. So this is equal to this. Forgot the minus sign. This outflow. And we're going to apply the divergence theorem and then turn this into the continuity equation. So a couple words here. Well, I said them. You guys leave some room. Put the required words right next to here. Good, so what do we have? Let's go ahead and write this out. We have minus integral, we'll take this into the integral, d volume is equal to integral. Now, you're going to apply the divergence theorem here. So this will be the divergence of rho v d volume as well. Right? At this point, we can have the same integral. We'll bring them under the same integrand. We'll have d rho dt plus divergence of rho v integral d volume. But since that's an arbitrary volume, we're going to require or conclude that the integrand itself must vanish, and that integrand being equal to 0 is our continuity equation. So there we have it. Continuity equation. d rho dt divergence rho v equals 0. Good. So conservation of mass gives us the continuity equation. Now, applications of this, well, we'll use it often enough later on for formulating certain problems. But first of all, we can just note that incompressible means that rho is equal to constant. So an incompressible fluid is one in which this term here vanishes. Rho is constant, can be pulled out, and therefore divergence of V is equal to 0. What else? Actually, we could analyze this thing a little more as well. Okay. Yeah. In fact, I'll leave that picture up. Because if you're just analyzing this fluid flow through this constriction, and there's clearly no fluid flowing through the solid walls of that pipe, it's just what's coming in and what's leaving. We have, out of this situation, I'll just write for rho equals constant, we have V1 A1 is equal to V2 A2. Oops, that's a A2. So I'll go ahead and label this thing. This is V1, there's cross-sectional area A1. This is cross-sectional area A2, and that's V2. So that's the really basic continuity equation that you will have had in that lower division book. And that would just be the direct application of this without going through with, any derivatives or anything. Good. And I'll add to this J rho V, the current density. We may use that sometimes. That's what you'll use in electricity and magnetism. Typically we'll have the density times the velocity shown. Okay, so we have that. Next we want to talk about force and pressure. Good, use this board. Next, force and pressure. I'll just remind us of the really basic definition. Force per area, Newton per meter squared, Pascal. And Pascal's principle is really that in a fluid, the force due to the pressure is equal to the pressure times area, so F equals P times area, and it's directed perpendicular to whatever surface of contact there is. Directed along a surface normal. So yeah, when you turn that into a vector, you're directed along surface normal. Okay, so that being said, let's talk about a volume element within a fluid. Okay, or a volume element within a fluid. And what I'll do is just draw that little cube. Okay. So there's our little cube. And of course it doesn't have to be a cube, but we're getting forces acting, on every face like that, pushing in on it, say it's subject to a pressure. We can formulate that force as an integral as well. So what we'll have is net force, basically my blue arrows there, missed a couple, right? Here, and there. So the net force is going to be equal to, leave a little space here, the integral pressure d area and the boundary of that volume. So it's area integral directed area right there. Now here's the thing. This is an outer surface normal, okay, and the net force from these inward pressures is therefore going to get that minus sign to balance that out, okay. This integral is in terms of an outer surface normal, and those vectors are pointed the opposite direction, okay. So it gets the minus sign there. And we could call that minus integral P n hat d area. So n hat's the outer surface normal. And that's why we have the minus sign. Outer surface normal. So next is an interesting trick that we do on this. We're going to scalar multiply it with a unit vector. And we're using Cartesian vectors right now, so if we multiply this with a scalar multiply with a Cartesian unit vector, then we'll get the ith component of that force. So multiply. Right here next, F net, that vector dotted into x of I hat, unit vector, equals minus integral P x I hat dotted into surface normal, the area, still boundary there. And now this is equal to minus the divergence. Okay, so now we have a vector. We have an expression to which we can apply the divergence theorem. This is going to be over V minus the divergence of P x I hat d volume. And that's going to be equal to minus volume dp dxi d volume. And put a star here. Note, at least leave some room in your notes. It's probably best because this is just a couple lines. Leave some room in your notes. Prove star by showing that divergence of scalar times vector equals gradient of the scalar dotted into the vector plus the scalar times the divergence of that vector. That's not hard to show at all. And in our case, this vector is a constant, which gives us this simple form. So yeah, if you just leave a few lines free, you can go ahead and take care of that. And then we'll have this relation. So what do we have? We now have f net ith component equals minus integral dp dx of I d volume. We're going to use this to apply Newton's law simply by treating this as an infinitesimal little volume, right? This was for any volume, but if we have an infinitesimal volume element, we'll be able to just call this delta V and move with that. Good, so that's our next step already. And now that we've found this, since this is just one component, we obviously have, coming back to the vector, minus integral gradient of P d volume. Okay. So good, we box around both of those. There's the component, and therefore we also have the vector again. Okay, send that up. Okay, so our next task is to interpret this in terms of Newton's law. So we want to have force equals mass times acceleration. Okay. But because there's a volume element, if we divide both sides by that little volume element, you could say we have mass times, we have density times acceleration would be equal to that integrand. So let's go ahead and put that down. And we'll call this Newton's law for Newton's law for a fluid element. Element delta volume, right? Or that's a volume, so delta M, that's our fluid element, would be rho delta V. Okay. That type of situation. So now we're going to use this equation right here to get Newton's law for that fluid element. Well, what do we have? Mass d velocity dt is equal to F net, so we're going to translate here. F net, it's got the minus sign still here. Gradient P, divide both sides by delta V. So here we go. Got from star. We have rho dv dt is equal to minus gradient of P. Just think of this little volume as being a delta volume element. Okay. So that M, should I have called it delta M, volume element? Doesn't matter. Okay. Here I'm just, this is just the pattern that we're following, M dV dt. So in this case our M is a little delta M, rho delta V. Okay. On this side we have minus grad P delta V. So they cancel from both sides. So yeah, this is fully right on. But it's not yet a field equation. Our idea was that, just write this, not yet a field equation. Our idea originally was that we were going to have V of X, Y, Z, and T. That means if, this board here is the field, or is the area in which the fluid is flowing, there would be this vector affixed to every point, and that vector could change in time. Here we're actually talking about a little fluid element being pushed around by a pressure gradient. So actually it's worth looking at this briefly. The minus sign will make complete sense. So I'll just put this as a note. So let's see what we're at. Not yet a field equation, because, well, here we go. Not yet a field equation for V of X, Y, Z, and T, because this equation star is really for a little droplet of fluid being pushed around. Okay. The star is for a droplet. I'll put that in scare quotes. A droplet being, pushed. Okay, I'm responsible for the formulation. Droplet being pushed around. Okay, that's Newton's law. Yet we want to convert it to a field equation. And that's not difficult to do. We have to look at this dV dt. So the next step is to obtain the field equation. Okay, good. How do we get that field equation? What we're going to do is treat this velocity of the droplet as this thing, and just take its derivative and apply a little chain rule. So now differentiate d dt of a v of x, y, z, and t. And we'll just do the chain rule on it. In fact, let's just do it for one component. Time derivative of v sub x, of x, y, z, and t. And we'll go ahead and take the explicit partial first. So there we have dvx dt, and then we'll have dvx dx. We do the chain rule, dx dt plus dvx dy, dy dt plus dvx dz dz dt. Okay. And now we're going to interpret these three expressions, dx, dy, and dz dt, as v sub x, v sub y, and d sub z. So now we have d dx dt plus, and look at what we have here. We can look at this as a scalar product where we're taking the gradient of v sub x, because it's dv sub x, x, y, and z, and dotting it into the velocity itself. So plus gradient of v sub x dotted into v. But we can just reverse the order of these two, right? The dot product is commutative, and that'll make it look a little more like what we're headed for. Plus v dot gradient v sub x. And now if we want to generalize this to the full vector, we just have to replace v sub x by the full vector. Let me think about my parentheses right here. V sub x, rad. Here, let's write it down first. So we have dv dt is now going to turn into dv dt partial plus v dot grad applied to v. I got a better way to look at it. This is going from the one component to all three. So this one is clear, that the three components here. Now the v dot grad, that is v dot write these all out. Oh, let's put it this way, because v dot grad, this is the way to look at that, is vx d over dx plus vy d over dy plus vz d over dz. Okay. That's the condenser. So we get vx d over dx. That's what we had here. Vx Yep. So yeah, compare these from the x component. You apply this entire thing to v sub x, and that's what we get here. So if we apply it to v sub x and get this, we apply it to v totally, then we get all three of those. So this here is the one you guys want to write out carefully. Again, leave a couple lines, make sure you get this, and then we'll take our next step. Because now we have this operation here on the left side, and we're ready to write down what's known as Euler's equation. Yeah, make sure you just collect all these terms and make the comparison. Okay. Very good. Okay, I'll go ahead and erase this. So now we have the field equation that we were looking for. And that is Euler's equation. came from. B dot grad applied to B equals minus 1 over rho gradient of P. So that's 3 equations for 3 quantities. We also have the continuity equation, divergence rho B equals 0. But you'll notice something. 3 plus 1 is 4 equations, right? This is scalar. But we actually have 5 quantities. So this is where the role of thermodynamics comes in, because pressure, density are thermodynamic quantities, and there can be other relations between them, okay, that have to be brought into play. Now there's another thing that hasn't come into this derivation yet. Let's see if I have this here. I'll just add the gravitational field for fluid in an external field, which is typically gravity, okay? Add that field. Remember, that field is an acceleration. These are all accelerations. Add G to the right-hand side. So then you have dv dt plus v dot grad v equals minus 1 over rho gradient v plus g. Because that's literally just the force you're adding, an external force you're adding to the right side of Newton's law. Okay, so no problem. And we'll see later that this can actually be incorporated into the pressure if you want to keep that simple form of just having a gradient of P there. So we'll get there soon enough. Now, have not really yet brought into play that this is an ideal fluid. So another note, this is an ideal fluid, i.e. no internal friction. No internal friction, that means no energy dissipation. And you see there you're in thermodynamics also, because energy dissipation would involve heat, okay? So the ideal fluid doesn't have that. And in that sense, one can say that the entropy in the fluid stays constant. Okay. Entropy stays constant along fluid flow. And so we can take an entropy per volume. We send this up using the board. Yeah, so directly underneath this, we'll take that entropy per volume. We'll have that stay constant as well. So that means S of X, Y, Z, and T is constant. And we get ds dt plus ds dx. Dx dt, same kind of chain rule I just did, a simpler situation. ds dy, y dt, dz dt equals 0. And this will be the gradient of S dotted into the velocity. for the S dt plus V dot gradient S is equal to 0. Now watch this. So if we put all these together, this, and this, we now have 1, 2, 3, 4, 5 equations and 6 quantities. So we can't win. However, these quantities, S, rho, pressure, will be related via some thermodynamic relation. Okay. So yeah, in the most complicated cases, one would make use of this. In the case of wave equations and stuff, you don't actually use this differential equation. You just use this relation here, the fact that the S is constant. Okay, let's see how we're doing time-wise. Okay, I think I want to wrap it up and just put all these things in one place, and that'll be it for now. Oh, and I'll put a little bit about the boundary conditions as well. Okay. So once more, we have, and I'll just put them in the order that we've derived them now. We have the continuity equation. That's a rho. Divergence rho would be 0. We have Euler's equation. V dot grad V minus 1 over rho gradient P. And I'll put in parentheses here plus G. And then we have this entropy equation. This is typically the most important part of it, but I'll go ahead and write this down. T plus V dot gradient S equals 0. So yeah, we got this complicated system of differential equations, any one of which could give us trouble. Boundary conditions. Are that V dotted into the surface normal equals 0 at a solid surface. Now what that means is that you can still have slip, but you cannot, of course, have the fluid going into the solid surface. So this is pretty important. So, at a surface here, let's go ahead and draw a surface. We can still have a tangential flow at the surface. But of course, we cannot have a normal component into the surface. So tangential, I don't know what we're going to call it, sliding at a surface. This is the big difference in boundary conditions between these ideal fluids and a real fluid in which V completely vanishes at a surface. So note, for a real fluid, and let's go ahead and write ideal up here for ideal fluids. For a real fluid, and that means it has viscosity. V is identically equal to 0 at a surface. Okay, so that's the difference between the two. Okay, so that's a decent derivation of all these things, it's thermodynamics that will link entropy, pressure, and density, but typically we don't need that much. The very interesting case of the incompressible fluid can simply operate with this equation. Okay, so if you have an incompressible fluid, I may as well write that down too. Yeah, this note goes under these right here. So also we're noting if rho is equal to constant, so we have incompressible fluid, then divergence of V equals 0. It's one equation, and then the Euler equation. Of course, the Euler equation, the vector equations, 3 equations suffice for P and V, which is those 4 quantities. Okay. So yeah, the incompressible case is very, very important. Okay, good. We'll leave it at that. Next time we'll jump into some basic applications. Okay, see you guys next time.